Okay, so we'll go back to another video. Here's a nice little infinite sum we want to calculate that actually involves with the Riemann Zeta function. We have that the infinite sum starting at n is equal to 1 to infinity of t to the power n multiplied by the Riemann Zeta at 2n minus 1 and then divided by n. So of course our parameter is that t's can be any real number in between 0 and 1, non-inclusive. So something like this is that we're actually going to do is, of course, we have a Riemann Zeta function, so we're actually going to be utilizing its infinite sum representation. So you can already tell that we're actually going to deal with something with a double sum. So we actually got to, do a little bit of manipulation and get a little creative on how to simplify things further. And actually, afterwards, eventually, we will actually be utilizing a nice trigonometric sign product, Euler's infinite sign product, to actually help reduce things a lot easier. And then we can actually, afterwards, get that nice little closed form that we want to achieve from here. So nothing much that needs to be said. So why don't we actually just jump right in? So what I can do first is take that n and then take that outside, so it'll be associated with the t to the power n. So then I have the infinite sum n is equal to 1 of t to the power n divided by n, and then the Riemann Zeta at 2n subtract 1. Then what I can do next is let's actually, as of course mentioned, we'll actually be utilizing its infinite sum representation for the Riemann Zeta function, and I'll distribute our infinite sum into the 1 as well. So then we have the infinite sum as n is equal to 1 of t to the power n, then divided by n, then multiplied with the infinite sum. So we'll just call this index m equals 1 of 1 divided by m to the power 2n, and then subtract the infinite sum from, of course, the same thing. So n is equal to 1 of t to the power n divided by n. So what you'll notice is that the last infinite sum term right here, this and actually comes to a nice little form of a natural log function series representation. This is the same thing written as negative ln of 1 minus t. And so of course that would be for that the absolute value t is strictly less than 1. Okay, so we can actually substitute this back for that. And then for this, what I'm going to do is I'm actually going to interchange our indexes. So we have m and then n of everything combined together. We can actually do this because both of these series actually converge absolutely. So we can actually combine it together into a actual double sum. So then we have the infinite sum for m is equal to 1, and then multiply with the infinite sum at n is equal to 1 of 2 to the power, or 2, t to the power n divided by n times m to the power 2n, and then subtract, so then minus, so then that'll become a plus the natural log of 1 minus t. And then next what I'm going to do here is that we have the exponents for n, so I will get that back together. So then we have the infinite sum m equals 1, and then infinite sum n equals 1. So then inside then that'll just be t, then divided by 2m to the power, or actually I meant to say n square, m square, and then to the power n, and then divided by n, so we still have plus the natural log of 1 minus t. So then, of course, with this double sum, with this sum over here, we can actually utilize, of course, that same definition at the natural log of minus natural log of 1 minus t. So we can substitute that back in. That becomes a minus. So then now we're just left with the only index of just m. So m is equal 1 of the natural log of 1 minus t, and then divided by m square. Okay, and then add this with the natural log of 1 minus t. And if I want to, let's just pick things up. Let's actually just move that to the front. So then we have the natural log of 1 minus t, then subtract the infinite sum. M is equal to 1 of, the natural log of 1 minus t divided by m squared. Okay, so then now here's an interesting note that we like to do here. So with the continuity, assuming with the continuity involved with this, we can actually change this sum of a natural log to write it as a term as a natural log of a product series. So then now rewriting this sum over here, so then note the infinite sum of m is equal to 1 of the natural log of 1 minus t divided by m squared is the same thing written as the natural log of the product series at m is equal 1 of 1 minus. So I actually can write this in terms of a square root. So square root of t, then positive, and then square, and then m squared. Okay? So with that being the case, you'll note that using Euler's infinite sign product, we know that sine of x divided by x is equal to the infinite product. So with n is equal to 1, I'll just call this n over here, of 1 minus x squared, and then divided by n squared times pi squared. So if we actually use our inputs correctly based on what we were working with, we can actually say that this is the same thing written on the top over here is going to be sine times pi times the square root of x divided by pi times the square root of x, and then set that equal to pi, or sorry, not pi, the infinite sum, the infinite product of 1 minus x divided by n squared. Okay, so therefore leading to say that the natural log of the infinite product series, keep writing parentheses like in and out like that. So then the natural log of the infinite product series, so that means m is equal to 1 of 1 minus, so the square root of t, and then square that divided by m squared, is then of course simply just going to be equal to, I'll just write this on the bottom, so then that'll just be the natural log of sine times pi times the square root of t, and then divided by pi times the square root of t. Okay, so then we're almost done. So then we have the natural log going back to earlier. So the natural log of 1 minus t, and then minus the natural log of sine times the square root of t. Well, let me first write pi and then the square root of t. Okay, and then on the bottom as well, pi times square root of t. So of course, applying natural log properties, so then this can be written as the same thing as the natural log of pi times 1 minus t multiplied by the square root of t, and then divided by sine times sine of pi times the square root of t. And we can actually simplify that even further. So actually, therefore, the final answer in this case, our nice little closed form for depending on our real number t from 0 to 1 non-inclusive of our infinite sum, is going to equal the natural log of pi times cosecant of pi times the square root of t, and then times the square root of t multiplied by 1 minus t. With that is our closed form for our infinite sum over there, with of course the Riemann Zeta function at every even input, with t with the parameter given as well, combined with everything that we've done with converting into a double sum, utilizing Euler's infinite sign product to get this nice little result over here. So yeah, that's pretty cool if you ask me.